Welcome to today's lesson. Let's begin with a quick recap on measurements and unit conversions, and why precision matters in science. Avoid these mistakes. When working with unit conversions, there are some common mistakes you'll want to avoid. Don't forget to square or cube your units when calculating area or volume. Be careful not to invert conversion factors. Always check whether your answer makes sense in context. A good habit is to ask yourself, is this result reasonable? Why precision matters. Precision is at the heart of science. Significant figures show us the precision of a measurement. It's also important to understand the difference between accuracy and precision. Accuracy is how close a measurement is to the true value. Precision is about how consistent repeated measurements are. Rules for significant figures. Here are the main rules. All non-zero digits count as significant. Zeros between non-zero digits also count. But leading zeros are not significant. Trailing zeros after a decimal point are significant, while trailing zeros in a number without a decimal are ambiguous. To avoid confusion, use scientific notation. For example, the number 123 has three significant figures. 1.05 has 3, 0.0032 has 2, and 4.00 has 3. Why this matters? This isn't just theory. It has real-world consequences. In medicine, precise dosages can save lives. In engineering, accurate stress calculations keep structures safe. Even in everyday cooking, conversions matter when scaling recipes. And in space exploration, navigation and fuel calculations absolutely depend on precision. So remember these takeaways. Units are critical. They prevent costly mistakes. Dimensional analysis is your best friend. Always check whether your answers make sense. And use significant figures to reflect the precision of your measurements. Above all, practice makes perfect. Now let's transition into one-dimensional kinematics, motion along a straight line. This lesson is designed for algebra-based physics students in PHYS 301. Over the next few minutes, we'll build a foundation that supports more advanced concepts. By the end of this lesson, you should be able to distinguish between scalar and vector quantities in motion, define position, displacement, velocity, and acceleration, apply kinematic equations to solve motion problems, follow a systematic problem-solving method, and interpret both position time and velocity time graphs. What is kinematics? Kinematics is the study of motion without considering the forces that cause it. In one dimension, we look at motion along a straight line, focusing on how position, velocity, and acceleration are related. This gives us the foundation for understanding more complex motions, using algebra rather than calculus. Motion is always described relative to a reference frame. We choose an origin, set positive and negative directions, and keep the coordinate system consistent. For example, imagine a highway. If the origin is mile marker 0, we define east as positive and west as negative. A car at mile 5 has a position of plus 5 miles. A car 3 miles west is at negative 3. Position tells us the location of an object relative to the origin. It can be positive, negative, or 0, depending on direction. For example, plus 15 meters means 15 meters to the right of the origin. Negative 8 meters means 8 meters to the left. 0 means the object is right at the origin. Displacement. Displacement is the change in position. It's a vector, meaning it has both magnitude and direction. Unlike distance, which adds up the total path traveled, displacement only considers where you started and where you ended. It can be positive, negative, or 0, and it uses the same units as position. Now let's talk about average velocity. Average velocity is defined as the change in position, or displacement, divided by the total time taken. In other words, it tells us how fast an object's position changes, not just how much ground it covers. For example, if a car moves from one location to another in a straight line, we calculate its displacement and then divide by the time. This gives us the average velocity over that interval. Remember, average velocity is a vector. It has both magnitude and direction. That makes it different from average speed, which only tells us how fast, without considering direction. Now let's look at instantaneous velocity. Instantaneous velocity is the velocity of an object at a specific instant in time. Think of it as the exact reading on your car's speedometer at one moment. On a position time graph, the instantaneous velocity is represented by the slope of the tangent line at that point. If the motion is at constant velocity, then the instantaneous velocity and the average velocity are the same. But if the velocity is changing, the instantaneous velocity tells us the object's exact rate of motion at that instant. Next, let's talk about average acceleration. Average acceleration is the rate at which velocity changes over a given time interval. In other words, it tells us how quickly an object speeds up, slows down, or changes direction during that period. We calculate it by taking the change in velocity, the final velocity minus the initial velocity, and dividing by the total time. Because it's a vector, average acceleration includes both magnitude and direction. A positive acceleration means the object is speeding up in the positive direction, while a negative acceleration, often called deceleration, means it's slowing down or moving in the opposite direction. So average acceleration gives us the big picture of how velocity changes across a span of time. Instantaneous acceleration. Acceleration tells us how velocity changes with time. Instantaneous acceleration is measured at a single instant, like what you feel during sudden braking. On a velocity time graph, it's the slope of the tangent line. For constant acceleration, the average and instantaneous values match. Scalars and vectors. Quantities in physics can be scalars or vectors. Scalars have only magnitude, like distance, speed, or time. Vectors have both magnitude and direction, like displacement and velocity. Scalars add with simple arithmetic. Vectors require us to account for direction. Let's look at a car that travels 100 meters east, then 60 meters west in 80 seconds. As a scalar, the total distance is 100 plus 60, or 160 meters. The average speed is distance divided by time, which is 2 meters per second. As a vector, the net displacement is 40 meters east, and the average velocity is displacement divided by time, or 0.5 meters per second east. 6-step problem-solving method. Here's a systematic approach. Step 1. Analyze and understand the situation. Step 2. Draw a diagram and set up a coordinate system. Step 3. List the knowns and unknowns with units. Step 4. Select the right equation. Step 5. Solve symbolically, then substitute the numbers. Step 6. Check that your answer makes sense. Problem-solving examples. Let's apply this to examples. A car accelerates from rest at 2.5 meters per second squared for 8 seconds. Using the equation for position under constant acceleration, we find the car travels 80 meters. That's a reasonable distance for the given time. Now imagine a ball thrown upward at 15 meters per second. At its highest point, the velocity is 0. Using kinematic equations, we find the maximum height is 11.5 meters, and the time to reach that height is about 1.5 seconds. Another example, a car traveling 25 meters per second brakes to a stop in 5 seconds. The braking distance comes out to 62.5 meters, with an acceleration of -5 meters per second squared. These examples show how the equations connect to real motion. Graphs give us powerful insight. On a position time graph, the slope is velocity. On a velocity time graph, the slope is acceleration, and the area under the curve is displacement. A straight line on a position graph means constant velocity, while a curve means changing velocity. On a velocity graph, a flat line means constant velocity, while a sloped line means constant acceleration. In summary, one-dimensional kinematics helps us describe motion along a straight line. By carefully defining position, displacement, velocity, and acceleration, applying the right equations, and checking our answers, we can confidently solve motion problems. Always remember, physics is about making sense of the motion we see around us.